Is there any problem in the problem set that you would like to, that you got stuck and I'm planning to discuss 6 problems today.
Okay.
Problem 6?
Yeah, 6 actually, none of us got.
Problem 6.
It's where we have to use isolating cuts to find.
Gary, you dress like summer.
Yeah. It looks like outside. So I didn't put on a jacket, but it was cold all the way here.
So today I want to discuss a problem, maybe give you some suggestion how to approach a problem that you got stuck at. And so I think one of the problem that people got stuck is 6B, is it? Okay. Is there any other things besides 6B? Oh wow, 6B is the only thing. Okay. Anything else at all? It's fine, we can discuss many things.
7, you have already discussed it in class.
Yes, 7 is something that, discussed in class, Just want to make sure that you can make things formal, Right. Okay, so 6B. So the first thing about 6B is that we can, we need to say that there is a subroutine that is similar to isolating cut that just discussed in class, but for vertex cut. So what do I mean by that? Suppose that input is the graph, and let's say you have a terminal set T. Okay, and what we want to do is that we can define, maybe I start by defining isolating cut. So yeah, maybe we can output for every terminal in T. For every terminal, we can output, maybe call it a separator for, maybe just to be clear, separator. Maybe like I do it like this. VS. So and such that so this is like for this is V, then it output this set together with its neighbor set. This is just a SV. Okay. Right. Such that LV contains V, like LV intersect T is V. So LV really just contains only V. Like it isolates V from the rest of the terminal. And SV is min separator. So you will output this thing for every terminal. So maybe SV might intersect, but LV will be disjoint. LV are disjoint. Okay. And then you can try to show that this problem you can solve it using log n max flow as well. Show can solve it using log n max flow. Right. So, is this something that you are like? Is this something that you have considered? You are doing this way? So we basically start from here, like try to prove isolating cut, but in the vertex version.
So does this also involve a similar output of SV star, like in the minimal?
Yeah. So, like, basically, you will need to kind of mimic the proof for edge isolating cut and make it work for vertex cut. Like, kind of go through the same thing and then prove this thing. Yeah. Okay. We will maybe we can go through this later, but suppose that we have this already. We can try to see why this is useful. Right? Okay.
Did we do something like epsilon modest vertices? We kind of treat all of them as a single terminal, so that we can separate them from other vertices.
Yeah, I'm not sure I got what you mean. Maybe let me point out where it seems to be a problem.
Maybe one related.
Mhm.
Here, since T, there need to be some constraint of T, right?
Oh yeah,
T is like the overall density.
that is true. That's true. So let's say that T is independent set. Like T, there are no edge between vertices in T. Okay. All right. So let's see. Okay. But is there any more question about the statement of this? Okay. So now, what we can try to do is this. So just to recall how we use isolating cut for finding edge min cut, right? So what we say there is that, okay, you have a graph, and then suppose that here is a min cut. Suppose that it contains like k vertices. Then if I just choose each node with probability like 1 over k, then it's likely that one of the node will be sample. Only one node in S will be sample, and every other sample node is outside S. So just by choosing probability to be 1 over k, like with some probability this event happen, and you can try several times. That let's assume now that you sample T is like sample with prob 1 over k. And now we have that like this is 1. Okay. But once we have this, we are done, right? Why?
We can find the separate.
Yeah, we can just, once we call, by calling isolating cut using this terminal set T, the isolating cut for this node V must be a min cut of the whole graph. Because this min cut is an isolating cut, and we find a minimum isolating cut for V. So this is good. We're good. Okay. Now let me point out something that seems to be, this is for edge, seem to be a problem for vertex case. So in the vertex case, now suppose that graph is like this, and let's say that this is a cut, and this is the mean separator S. So if somehow I sample a vertex, if I sample a terminal set such that only one node, there is one node. If I sample terminal set T, if somehow, if this thing is 1, but this thing is 0, then it's good. If I sample a terminal here inside L, but other terminal is outside, but nothing is in S, then it's gonna be good, right? Because I can call this thing, and this like a yeah. So like and if T is independent, set. Yeah. But this one is kind of quite easy to ensure, because like if they are not independent, like if it turns out somehow that V is in here and nothing here except V is in T, if these people are not independent, you can just prune some of them out. Let's say remove this, and now they are independent. And we don't really care about the terminal set node outside S and L. Yeah. So this is quite easy to ensure. But what we really need is this two case. What I want to point out is that if you don't have this case, then this is a problem, right? Because if there are some node T, some node terminal inside S, then the isolating cut for V, the vertex isolating cut for V, will need to avoid this guy. So it will return some cut that avoid this guy. And this might not be a min cut anymore, because there are more constraints for the min isolating cut for V. Does it make sense? Okay. Good. So what we really need is that we want to ensure both of these. Okay. And this is gonna be not too hard if like not too hard is like, suppose that size of S and L are kind of the same. Let's say both of them of size K. Then what would you do to get T? Yeah, we would just sample with probably 1/K again. Like likely it will likely that, okay, with some constant probability, you only get one node in L and nothing in S. Yeah. But this may not happen in general case, right? It can be the case that the min vertex cut in the graph, it might look like this. It might look like L might be like this, contains just constant node, and S like this, like n nodes. And this looks like a problem, because if we want to avoid everything in S, then we better sample with probably like 1/n. But once we do that, to get any node in L at all, we might need to try like n times, so that like we get some node in L. So because of this, it seems like you need to try a lot of times. like n times, and that now like for each time that you try, you call isolating cut, but you need to call isolating cut n many times, so that's slow. Okay, and this is why we will use 6a. So what does 6a say? It says this. So first of all, if the size of the min cut is at least 1 minus epsilon min degree, then it's going to be very easy to return min cut, right? Approximate min cut. Just return the min degree and you're done. So let's assume that is not the case, and this is what happened in 6a. When this is not true, when like min cut is less than min degree by quite a lot, then it says that actually there is a min cut such that L is not too small compared to S. So this situation cannot happen. We will have that the size of L. So if kappa is less than delta by quite a lot by this factor, then L is not too small compared to S. All right. And once this happens, then you know that. So suppose that this is K and S is maybe if S is K but L is epsilon K. So if you sample with probability 1 over K, then you avoid everything in S with some probability. But if you try like 1 over epsilon time, then one of the terminal will be in L now.
We also need at most one vertex in L.
Yeah, so like if you sample with probably 1 OK, then it's gonna be like one vertex in L usually. So my claim is that if this is true, and you sample with 1 over K, then the probability that T intersect L is 1 and T intersect S is 0, this thing is something like epsilon.
But RK, we only have a lower bound on that.
Say it again.
If we only have L, it at least epsilon itself.
Oh, right. So, okay, good. Sorry. So okay. I should say that I mean, if L is bigger than S anyway, then we will sample with probably like 1 over L. Yeah, right. So good point, but
I think you can sample with probability 1 over L plus S. And then you can.
right. That would do it, yes.
Yeah, but the problem is how do you guarantee that there is at least a vertex in R, in the part outside L plus S?
Yeah. So, I mean, let's see.
As long as you sample at
Yeah.
If the thing might be things that don't have that is very large. Maybe in the moment.
Here,
So you will always assume that R is as big as L, but when R is as big as L, so let's see, like if this is L, if L is like something like epsilon n, and this is S is like something like n over 2 or something, and this is R is like epsilon n. Let's see. One second. This is a good point. Okay. So you can assume for now that this is less than 0.9 n, just to bypass this. How to So if this is less than 0.9 n, then this is gonna be like at least like 0.1, 0.01, something like n, and you are fine. But right, you are fine. Do you? Sorry, but even if this is like, even if R is like epsilon n, and this is something like n, isn't it the case that if you try something like 1 over epsilon square times? Right. Thanks. Oh no. Good, very good. Sorry about this. Yeah, I'm okay with epsilon square. Very okay with that. Yeah. So do you kind of roughly see that once you have this subroutine, then we are done? Should I clarify more about like what to do once we assume this before I go into this subroutine? Yeah, please really feel free to ask.
And I think more convenient way to make T is an independent set is just remove the edges between vertices in T. It will be a little bit simpler.
Yeah, yeah. Yeah, we can remove edges between T. Yeah. Okay.
Can you repeat what happens to the last case?
This case? Yeah, so the reason we talk about this case is just like the question was, how do we even make sure that like at least we get some other node which is not in S, and we need some other node in the other side in R. Okay, and most likely when most of the time when we think about L and S, like L is on the smaller side, S is on the S is separator, and this is R. When you think of R as something like the rest of the vertices, most likely when you sample set of vertices, like there will be actually a bunch of guys in R anyway. So we don't really be very careful like whether we get any nodes in R at all. But in the extreme case, is that when S and L is so big, then R can be not so big. But what is that extreme case? Is a case when S is as big, almost as big as L. When S is this big, we know that L is at least epsilon n, but we assume that R is as big as L, so R will be like epsilon n too. When this is the case, if you sample, if you sample T is sample with probability, like with prop something like 1/n. Yeah, then you know that like the probability that T intersect L is 1, T intersect S is 0, and T intersect R is at least 1. This thing is going to be something like epsilon square. Basically in expectation, the expectation, in expectation you sample like epsilon guys here, and you expect to sample something like epsilon guys here, and this is just like making it precise, I guess.
What if we sample with probability 1 over epsilon?
Then it will be very likely that you sample some node in S.
But I guess, according to our previous discussion, we need to sample with probability 1 over L instead of 1 over X.
So, sorry, I should say that we should sample with probability 1 over S plus L. This is gonna make it work because or you think of max of S and L. Yeah. When L is very big, you sample with probably 1 over L. But if S is bigger than L, then you sample with probably 1 over S. Yeah. like when L is much bigger than, like the goal is really just to avoid everything in S, right? And if L is bigger than S anyway, if you sample with probability 1 over L, you will avoid things in S. But if S is bigger than L, now you need to sample with probability 1 over S.
If you sample with 1 over S, then still we can be bound the probability that 1 belongs to L.
Yeah, we could. So this, yeah, as long as L is at least epsilon fraction of S, then the probability is going to be something like epsilon. Yeah.
Where does the approximation comes from?
The approximation comes from here, come from the fact that we can guarantee that L is at least epsilon S when you know that mean cut is less than 1 minus epsilon delta mean degree. So what would you do is just like if mean cut is very close to mean degree, then you can just return mean degree.
No, so do we have to use isolated class? If like there is maybe a super easy algorithm, like if the mean cut is less than 1 minus epsilon mean degree, we can just return the mean degree, right? If it's larger than that, then L and R are larger than constant proportion of S. So we just sample like pairs, and we can do and code the mean max flow, and then we have like constant probability to get the mean cut.
So when this thing happen, it's not clear how to just sample a pair, because when this thing happen, it's true that L is as big as S, but all of them can still be very small. Like this can be L, and this can be S. And if you want to sample just a pair of nodes, you need to sample one node in L here and one node in R. But to just get some node in L, like if you just sample a pair, it's going to be hard to just find this guy in L because L is so small.
L is larger than epsilon S.
Yeah, but S can be small too. Let's say that S is 10, L is 1. Right. What we do here instead is, okay, if all of them are small, we will just sample a bunch of guys actually, but only one in L and nothing in S, and we call isolating cut. Okay. All right. Right. And to prove this, there is really no trick here. Like it's really just kind of go through the material and see that, okay, this thing works. Like submodularity of cuts doesn't just work for edge cut, but it works for vertex cut, and just go through it. Yeah. So. Okay. So that's 6B. And for 6C, well, basically, you will try to sample proportion to the weight. like a node that have a large weight will be sampled with higher probability and so on. So once you have done 6B, then for 6C, just sample with respect to weight. And like you can prove 6A for the weighted case too. Basically, if the weighted mean cut is much smaller than mean degree, weighted mean degree, then like the weight of L is going to be at least the weight of S. So it's just kind of go through. Yeah. Okay. All right. More question about other question, other problem? Sorry?
5A.
5A. Okay. So 5A, sure. So okay, here, suppose that maybe I call it T just to be, yeah. So suppose that the graph look like this. Let's say that this is the mean cut. This is S and L and R. Okay. And if you choose like T, K plus 1, and S is of size K, right? K is, let's say K is a mean cut. Yeah. Now if you choose K plus 1 guys and the pairwise like K plus 1 node and the pairwise connectivity between this set T are larger than K. Can it be the case that the set T looks like this? No, right? Because otherwise these two guys will have mean cut less than K. So we know that T will look like it either be here or here. Right. And now, so let's say that T is here. So we know that T is on L union S or S union R. So let's assume it's the first case. So here's a hint. Consider this graph where you add this super source, connect it to everyone in T, and consider this graph. Yeah, this is a hint. Yeah. For example, if you look at another node T here, and if you compute ST mean cut, ST vertex mean cut in this graph, what would be the result? So, like, can the vertex mean cut be larger than K? That's not the case, and you will use this. Right. So that's like the hint for 5A. Yeah. Anything else? Any question?
Maybe you give a hint for 3A.
3A. Sure. Yes. So, 3A. So, okay. Well, we are in the situation where, like, we were thinking of you have a seed X, right, and call this thing L. So and the volume of L is like nu, and there are k edges going out here. Okay. So consider the algorithm in class. The algorithm in class is that we will do some depth first search or some search, basically breadth first search or depth first search, such that you explore new k edges, and you explore new k edges. Maybe you might go in and go out here, but it's new k. And once we do this, then if you sample just some edge among the guy that you explore, then with probability like 1 minus 1 OK, you will be outside. And so if you do this step like k times, then it can you can say that like with some probability, like constant probability, every time that you sample, you get something outside L, and that's good. Now, if you don't care much about exact, like, so suppose that I just want 2 approximation, maybe. What if I say that instead of explore new k, I explore like 10 new? Yeah. Then you will be like outside with probably like 90%, right? So it's like instead of going like you get some guy outside L at every iteration, you get some guy outside L like 90% of the times. So it means that if the number of edges here is like it's less than 1.9 k, then because if you repeat k times and you get out 90% of the time, if this guy has size less than 0.9 k, then you got stuck. Like you will detect this cut if this thing is small enough. If it is like larger than 0.9 k, you might not detect this because you only you sample the guy outside only like 0.9 k times. But that's fine because we are okay with approximation. Yeah. So that's the Does it make sense? Yeah.
I think so.
So the point is, try to explore less than new k. And now we don't need to, now once you explore less than new k, but only like maybe nu over epsilon, then only like 1 minus epsilon fraction of the time that you sample, you'll be outside. But that is fine because we are okay with 1 minus epsilon approximation.
We need some large amount. So as long as 1 over k, and this is just the exact.
Yeah, when epsilon is 1 over k, then it will be exact. So basically, like 3a here is really like generalization of the exact algorithm.
How do you know, like, you get outside of 0.9 k times already?
So,
Before we get stuck, we don't know what k is.
say it again, sorry, I don't.
Before we get stuck, we don't know what k is.
No, k is given. K is given here. K is given as a parameter, right? Did I say that we are given k?
We have this one.
Yeah, we have a promise. Yeah. Okay, so what I say here, maybe it should, like I kind of flip the things.
It should be 1.1k.
1 by 1k, 1 by 1k.
Is it 0.9? Like the cut that we return is
1.1k, you mean?
yeah.
So, I mean,
So how many times are we repeating the iteration?
so yeah, I mean, maybe if this is really about k, then we should say that suppose that we are okay with 2 approximation, then we repeat our algorithm, like the number of iteration will be 2k. Yeah.
So it should be 1 plus epsilon k.
1. Yeah, 1 plus epsilon k number of iteration. Yeah. Right. Yeah. So this is the number of iteration that you should try, but you explore less number of edges. Yeah. Okay. Other question? Which one is the hardest?